So let's see, this is a corner of a corner of kinds of things that I do. And I was just pleased to find out that there's a community of people that cares about finite models, because at least, well, several times in my life, I've been able to discover really interesting things, I think, using finite models. And I thought you guys might find it fun to hear about those things and maybe to give some feedback about better ways that one can think about some extensions of these kinds of things. All right, so let me start off. So let me tell you about a thing that I discovered 22 years ago now that was sort of surprising to me. Okay, so here's the story. So I was interested in logic. So the question is about the axiomatization of standard Boolean algebra. And, 1847, George Boole has his original sort of Boolean algebra. People clean it up. They get an axiom system for Boolean algebra. It looks something like this. Then, as everybody here knows, around 1900 or so, people realize you don't need and or not. You can just get away with Sheffer stroke NAND, whatever you want to call it. And so by 1913, Henry Sheffer had this axiom system for Boolean algebra. The thing I was interested in was, what's the very simplest possible axiom system for Boolean algebra? Why did I care? Because I was interested in, if you think about all possible axiom systems, I wanted to know the axiom systems that we humans have chosen to use to do the mathematics that we do, where do those lie in the space of all possible axiom systems? Are the axiom systems that we chose to use somehow very low-lying axiom systems in the space of all possible axiom systems, or are they kind of randomly placed and so on? So as an example of that, I wanted to use Boolean algebra, and I wanted to find out, where does the minimal axiom system for Boolean algebra lie in the space of all possible axiom systems? Okay, so to continue with this story, so Sheffer, 1913, finds this axiom system for Boolean algebra. Then, Lukasiewicz winds up in Ireland in 1947, and a chap called Carew Meredith goes to some lectures he's giving, and Carew Meredith takes it upon himself to try and find a minimal axiom system for Boolean algebra. So in 1949, Carew Meredith finds this axiom system for Boolean algebra. Then he works for most of the rest of his life trying to simplify that axiom system for Boolean algebra. By 1967, he gets to this one here, and 1969, he gets this one here. So that's where things had sat since the 1960s. And so I was curious, could one do better? And I had reasons to believe that there might be a really pretty simple axiom system for Boolean algebra, because I'd spent a lot of time trying to study how simple programs, what behavior simple programs can have. And it's a different topic. Let me not get deeply into that here. But the sort of the big result had been that even very simple programs that I studied, particularly cellular automata, but later Turing machines and other kinds of things, even extremely simple programs could have very complicated behavior. So that kind of gave the intuition that maybe even a very simple axiom system could at least have the richness of Boolean algebra. Okay, so what did I do to try and find the simplest axiom system for Boolean algebra? Well, I used at first finite models. So it's gotten a little bit easier to do that kind of thing now. Let me just find, sorry. Let's see. So this is just sort of a modern version of what I was trying to do. So here's just a function that gives us, given the axiom f of AB equals f of BA, this is giving us the set of finite models of size 2, it's defaulting to size 2 here, the set of size 2 models for f that satisfy that axiom system. Okay, so for example, we could, if we wanted to, we could just do, we can just plot the multiplication tables for those models of that axiom system. Okay, so maybe we try a different axiom system. Let's try the axiom system for semigroups. Here we go, and we could, this would now give us the, let's just do this here. This would give us, oops, this will just show us the, should show us the multiplication tables for size 2 semigroups. So maybe we can just go here and just change that. Let's make this size 3 semigroups, and now it'll take a bit longer, but there are the multiplication tables, the finite models for that particular axiom system there. Okay, so very concrete stuff. So now the question is, how do you go searching for the simplest axiom system for Boolean algebra? Well, the answer is you just enumerate axiom systems and you kind of try to prune them by looking at which axiom systems of the ones that you might enumerate. So we could just go ahead, for example, let's see, how can we do this? This is a convenient way to enumerate axiom systems. So let's say we just say here, this just says find all possible sort of tree structures. Let's see, we could probably just show you the tree structure here. Okay, so find all possible kind of tree structures with F a binary operator where the leaves are A, B, A, C. Okay, so that's going to give us, so now to make axioms, we can just say something like, we can just say this thing here equals A, for example. And that will give us a collection of tiny axioms. And so then what we want to do is go through that collection of tiny axioms and figure out which of those, what models those tiny axioms have. So if those tiny axioms have models that correspond to the multiplication tables of NAND and NOR, then they are plausible models for Boolean algebra. If they have multiplication tables if they have models that correspond to all kinds of other Boolean operations, then they're not plausible axiom systems for Boolean algebra. Okay, so that's the approach. So then what happens is, well, here's kind of the result. If you just go through and you look at things as a function of the number of variables, as a function of the size of the number of NANDs, the number of branches in the tree, basically, you just keep going, and you're saying, let's say we have 2 variables and we have the number of NANDs going up to 6. We can say the number that allow only NAND for size 2 models. Okay, there are 76 possible axiom systems that allow only NAND and NOR for size 2 models with 6 variables. 6 NANDs and 2 variables. Okay, then if we try doing things with just 2 variables, we eventually find out that there just aren't any. We can exclude just by enumerating finite model, by computing the finite models, we can exclude the possibility that any axiom system with just 2 variables can give us Boolean algebra. Okay, so let's keep going. We keep going and we look at 3 variables, and we can just start enumerating more and more possible axiom systems that involve 3 variables and larger numbers of binary operators. Okay, so if we keep doing that, we find that we can prune things down by using, I think I got to size 4 models. And what you get in the end is 25 inequivalent possible axiom systems. Okay, they're the left-hand side, so they're all equals A. So let's just make that those are the possible axiom systems. So now if we take one of those axiom systems, it's better be the case if I didn't mess this up here, that if I feed that into the finite models system, let's see up here, let's try doing that. Finite models here, let's go down here, okay, and let's feed in this first example here of a candidate axiom system, and this should give us of size 2 finite models. Oops, what did I do wrong here? Oh, silly me. Okay, I have to say there. Just trying to extract the thing that actually corresponds to. Okay, there we go. So there at size 2, that axiom system has just those 2 models which correspond to NAND and NOR. Those are the multiplication tables of NAND and NOR. So let's try just to see whether we can establish these things. Let's try size 3 models. Hopefully we won't find any models that work here. Okay, there we go. There are no models of Boolean algebra of size 3. Whoops, what did I just do here? But if I go and I try, let's say, size 4, I should get some models of Boolean algebra at size 4. That might take a little while to do the model checking for that size here. I should find so basically this is the approach, is just to prune the space of all possible axiom systems by looking for finite models. You end up with these 25 candidates, and then, well, what do you do then? well, then you actually use automated theorem proving to find out, and this is actually, I believe, remains the only unexpected, not known in advance thing that's ever been found with automated theorem proving. I think most automated theorem proving is, validating things you sort of already knew were true. But this was a case where I was looking at all these 25 possible candidates for Boolean algebra. And I think I might have to kill this thing. I should have told it to do this in parallel. I was just doing this on one machine, which was a mistake here. All right, we're not going to get. Well, let's leave it for a second here. So in any case, the idea was to take those candidates found by pruning by finite model theory, so to speak, and then use theorem proving to nail the final thing. So okay, so the final thing is that you find that, let's see if I can, that axiom system is, that single axiom is an axiom system for Boolean algebra, and it is the simplest possible axiom system for Boolean algebra. And I know that because I enumerated all the other ones and none of the other ones work. So this is kind of the end of the road, so to speak, in terms of what is the simplest axiom system for Boolean algebra. And it was something that basically I thank finite model theory for providing kind of the raw material to be able to find that. Now, just for fun, perhaps we can look at what it looks like to do the proof. So here's we can just take that axiom system, and let's not prove let's say Scheffer's axioms for Boolean algebra. Let's just prove commutativity of NAND. So now we can grind away here, and this is just using automated theorem proving under the hood and inside Mathematica. And here's the results. And now, for example, let's say we can ask for the proof graph, and this will show us the interdependence of lemmas in the proof of that particular result. It's a somewhat long proof. It's 102 steps. An interesting feature about that proof is, I printed that proof in this big book I wrote called New Kind of Science that came out in 2002. And it's in 4-point type or something across 2 pages, and it's a ridiculously human incomprehensible proof. And so far, a number of people have tried, including myself. It's really been impossible to find kind of human waypoints within that proof that allow one to actually turn it into a kind of human understandable narrative. It's kind of like the innards of some machine learning system, where the machine learning system identified certain features, but we don't have sort of words for those features. We don't have a way to describe it. So similarly here, the intermediate lemmas, while we can do all kinds of things like say, well, what were the popular lemmas and so on. I think this one here has a picture of kind of which lemmas were the key lemmas in doing this proof. We still don't have kind of a human way to describe what's going on. Okay, so that's a little bit of a story about a use that I made of model theory, finite models. Let's talk a little bit more about kind of let's talk about the sort of the second big thing I wanted to discuss. Let's see, I can show you one more thing here. This is kind of an empirical metamathematics of the world of axiom systems, sort of viewed from a finite models perspective. So this is just looking at possible axiom systems here, and this is looking at their models of size 2, 3, 4. And it's kind of interesting to see to what extent models that things that, like, there's semigroup theory. I think that's commutative, that's abelian group theory. And so one question would be, if somebody just showed you all possible axioms and they gave you kind of the model signature of all those possible axioms, could you pick out which ones are the axioms that we humans have decided were useful? In a sense, having a small number of models is the statement that that axiom system is actually about something. That axiom system has, there's a small number of things that we can sort of say it's about this kind of object, rather than just it's describing a whole range of different kinds of things. I never managed to find any kind of signature in the world of models for what axiom systems humans would have picked. I have to say that one of the surprises I did find was in terms of theorems that people pick, like in Boolean algebra, for example. There's this sort of question of all possible theorems of Boolean algebra, which ones are given names in textbooks of logic. And it turns out there is a way to, there is kind of a an objective way to decide what that should be, which surprised me, which has to do with theorems that, if you enumerate the theorems of Boolean algebra, all theorems of Boolean algebra in lexicographic order, the ones that cannot be proved from ones earlier in the list, so they essentially provide new information in this lexicographic sequence, those are the ones that get given names, basically, with one exception to Morgan's laws is one that can be proved, but is still given a name, but the proof is rather long, from earlier axioms. Okay, let me switch gears a bit and talk about another kind of way in which I think model theory has sort of finite models have an interesting, provide an interesting perspective on something. So one of the things I've been interested in, as I mentioned, sort of simple programs and what they do. And look, I just have to show you because I somehow, this is the sort of my favorite simple program. Here, let me, this is a cellular automaton. This is, here are its rules, very simple rules. Yet, if you run those rules, starting just say, let's say from a single cell initial condition, let's run those rules for 100 steps or something. This is what we get. And if you keep going, you'll find the thing keeps generating complicated stuff. Okay, so that's led me to all kinds of explorations in science. But one of the things that's kind of a tantalizing thing is once you see that from such a simple rule, you can get such complicated stuff going on, you ask yourself, well, what about physics? What about the whole universe? And so I thought for a long time about this, and finally about 2.5 years ago, made some really rather, I think, rather spectacular progress, which seems to have turned into a sort of fairly big effort in some intersection between foundations of math, foundations of physics, and foundations of computation. But this is this sort of big effort of our physics project, where we seems like we've actually managed to find a pretty good idea for what sort of the machine code that underlies the physical universe is actually like. And this is not my time to talk about this, but suffice it to say, it's kind of at the bottom, it's a bunch of hypergraphs being rewritten, and the results of that on a large scale, like, you know, molecules bouncing around on a small scale give you on a large scale fluid behavior. On a large scale, these hypergraphs being rewritten give you the structure of space-time and Einstein's equations and so on. And the fact that there are multiple paths of rewriting is what gives you quantum mechanics, etc. Okay, one of the things that's interesting about this is you end up with this kind of mathematical structures or computational structures that are the results of kind of doing all possible rewritings, essentially running all possible computations from all possible initial conditions. So think about Turing machines. You're thinking about running all possible Turing machines from all possible initial conditions for an infinite time. The object that you get from that is a thing we call the ruliad, and it's a non-trivial object because of equivalences between results, states that you get from these Turing machines. Okay, so having said that, what we think is that that ruliad object is the underlying thing in the end in the physical universe. And basically our perception of physics comes from the particular samplings we make of this ruliad object. Okay, so now the question is, well, what about mathematics? What actually is mathematics underneath? And is it in fact just another instance of this ruliad object? Okay, so this is where things get quite funky. So let me quickly try and show you. Let's see, where's the best place to start? Okay, so let's talk about sort of a meta model of mathematics. You just think about, you know, you have some axiom system here, and you're just doing rewrites, let's say on expressions here. You're rewriting them, and what you're finding is, you know, you make some complicated set of rewrites. These are expressions that are related by the axioms, and then something like a theorem is the presence of a path from one expression to another expression. We can write out the proof of that theorem, which corresponds to the path. It quickly gets much more complicated. There's another theorem represented by the two endpoints, so another path that corresponds to the proof. Okay, so if we think about kind of generating sort of in, we think about generating all possible proofs, all possible theorems, all possible proofs. And we start asking kind of how does that how does that work? Well, let me show you something here. So just as I was talking before about finding axioms systems, let's see, here's which one is this? Oh, here we go. Okay, so we can start doing this is okay. I'm eliding some technical issues about the difference between theorems giving theorems versus expressions transforming into expressions with axioms. This is basically what's happening here. Let me maybe show you a slightly simpler example. Here we go. So this is a case where you've got two theorems. This is a rule of inference, basically. This event is the combination of two theorems giving another theorem. And so this picture is showing you, starting from these green axioms, this is showing you, this I guess is for monoid theory or something. This is, or maybe this is a piece of group theory. This is showing you from the axioms, what theorems do you get? Okay, so you can build up this giant entailment cone of what theorems can be derived from underlying axioms. So here's one of these for a version of Boolean algebra, and we can ask the question, in that giant entailment cone of all possible theorems that we can derive, where are some theorems that we care about? This is kind of what we've got here. Is this is sort of the structure of space, and then this is the kind of the geography, the human geography of where did we colonize, where did we populate in this mathematical space. So anyway, we can go and when we try to find paths, that's another example of finding some actual theorems we care about in this kind of mathematical space. When we do automated theorem proving, what we're doing, this is a very sort of inefficient way to find theorems. We're just generating all possibilities and finding places where we run into things we care about. With automated theorem proving, we're sort of systematically finding paths through that entailment structure. And so, for example, well, I think that's the proof of that Boolean algebra result, just drawn in a slightly nicer way. Okay, oops, that's not what I wanted to show. Well, that's actually interesting in its own right. That's a couple of pages that show the standard axiom systems that one uses in standard mathematics, so to speak. It's kind of interesting how small that set of axioms is in the space of all possible axioms. Okay, models. Well, all right, one of the things that one can do is to say in this entailment structure, so this is just a simple example of some models. The question is, we have this entailment structure, and we have to ask, well, how do models relate to this entailment structure? In this entailment structure, we've got a bunch of proofs. Models give us a way to sort of group together pieces of those proofs. So here, for example, we have something, this picture is kind of a model theory meets proof theory picture. What it's showing is, for this particular model of this operator, of this binary operator, this is showing that the colored blobs correspond to things which are equivalent according to that model, and the lines are joining things which are equivalent according to proofs which are provably equivalent in. Let's see. This is based on some underlying axiom system. So it's kind of showing, in some sense, what we can think of is that the models are, in the end, turn out to be kind of transversals to this kind of structure that is this entailment structure generated by applying laws of inference to get proofs. The models correspond effectively to picking slices across that entailment structure. And well, I don't have too much time here. So let me just say that the thing that's rather interesting about that is that this business about kind of slicing across entailment structures, it's the same kind of story as slicing across. Entailment cones in mathematics are like light cones in physics. Entailment cones are things where things are derivable by applying laws of inference. In physics, the analogous thing is that the next state of the world is derivable by the application of a rule to the previous state of the world. And the influence of one event, one rewrite on other rewrites, defines this light cone of which events can be affected by which events. And the slicing across those light cones in physics corresponds to reference frames. well, they're space-like hypersurfaces. They're surfaces that define simultaneity in physics, because in a sense, the every kind of time corresponds to this. Well, the analog of time in the metamathematical case is the application of these laws of inference. And what one's doing is one's saying there's this kind of you're asking for things which can be considered, in the case of physics, can be considered to happen simultaneously, that's how you set up reference frames. It's ultimately a foliation of this, well, causal graph that you get, and you can do the same kind of thing in metamathematics, and models play the role of reference frames in physics. The corresponding thing in mathematics is models. This is not fully worked out, but I'll show you a few other bits and pieces. So this is kind of a picture of sort of empirical metamathematics picture. These are axiom systems down the left. These are theorems across the top. And this shows which theorem can be proved. Obviously, these are equivalent kinds of things, but which theorem can be proved from which axiom system. And so now we can ask, if you do that using models, you can ask, well, what do you find by using, I think that's size 2 models, size 3 models, and so on. And it's kind of interesting to compare what do you deduce from different kind, what equivalences can you deduce from models versus what equivalences can you find by doing the ultimate kind of proof that you do. So maybe I've got some other pictures here. That's just another version of the same kind of thing. Maybe I'll just show you a couple of other things perhaps of interest. I mean, there's a whole world of kind of studying the topology of proof space and looking at and it's very related to things like these proofs are very much like game graphs. So for example, if we have, I don't know, this is Towers of Hanoi, this is the game graph for Towers of Hanoi, and this we're seeing kind of topological structure here, and that is sort of a simplified version of the topological structure that you see in proof space. All right, just one other thing here. Let me just can show you something about kind of in this kind of world of doing of looking at sort of empirical metamathematics. Well, you can, for example, you can just look at Euclid and you can say what is the structure of what theorem is proved from what axiom in Euclid. There's a tiny fragment of Euclid, that's all of Euclid, showing at the top the original axioms and common notions of Euclid, and then the very bottom theorem is the fact that there are 5 Platonic solids. But that's the structure of the kind of proof interdependent, the theorem interdependence for Euclid. Well, so one question you can ask is, in this sort of metamathematical space of all possible theorems and so on, you can ask questions about where different things lie. This is using a kind of one of the proof assistant systems. This is the proof of the Pythagorean theorem from set theory, and it's kind of a complicated mess. And it kind of, and you can do things like you can say, well, where do in the sort of in proofs that have been written down in proof assistant systems, where do different areas of mathematics lie? Where do some famous theorems of mathematics lie in the sort of space of all possible theorems, or at least in this definition, in the structure of proof space and so on? Well, all right. I suppose one last bottom line, and I should stop here. Okay, I think there are some very interesting things to be understood by thinking about models as reference frames in metamathematics. Just to give you an idea of sort of what the sort of physicalization of metamathematics looks like. This is a big effort of mine that came out earlier this year about the physicalization of metamathematics. Here's a non-trivial fact about mathematics, that when we talk about the Pythagorean theorem, for example, we can just start talking about the Pythagorean theorem, or we can do mathematics at the level of the Pythagorean theorem. We don't have to do what the proof assistants might want one to do and dive all the way down to the axioms of set theory and say, how are we defining the real numbers, you know, this or that. It actually doesn't matter. When we deal with the Pythagorean theorem, there may be different definitions of real numbers that we might use, but actually at the level of human level mathematics, all those microscopic details don't seem to matter. So the question is that surprising that there's kind of an emergent kind of higher level mathematics that floats far above the kind of microscopic molecular dynamics, so to speak, of all of these very precise axiomatic kinds of inferences and so on? Well, this situation is very similar to what happens in something like thermodynamics, where you have all those microscopic molecules bouncing around, but you manage to find at a high level things like the gas laws or the laws of fluid dynamics, which don't depend on those microscopic details of all the molecules bouncing around. Well, it turns out in physics, one of the big results of our physics project in recent times has been that the fact that sort of continuum space emerges for observers like us. It matters that we are observers who aren't diving into sort of the computational details of what's going on. We're insisting on keeping things computationally bounded, so to speak. For observers like us, we sort of inevitably conclude that there's kind of a structure of continuum space. And so the bottom line result is the fact that observers like us, with the characteristics of humans with computational boundedness and the important property that we believe we are persistent in time, even though we are made from different atoms of space at every successive moment in time, those two assumptions, those things that characterize observers like us, necessarily give us the continuum structure of space with lots of physics details about that. And the claim is that those same characteristics of observers like us also are what let us look at this giant mess of metamathematical structure and operate on it by thinking about mathematics in this sort of high-level way and talking only about the Pythagorean theorem rather than diving down to all the details. Well, there's lots more that I could talk about, but I just wanted to mention those things, and I thought there's sort of there's all kinds of fun stuff about the analogy between physics and things like black holes. Black holes in physics correspond to decidable theories in mathematics. Black holes in physics are places where, in our model of physics, basically the rewrite rules that define the progress of time eventually stop applying, and so time stops. That's the characteristic of a Schwarzschild black hole, for example, is that time is finite, and there's an end to time inside such a black hole. And it's the same kind of thing in metamathematics. The analogy is that you end up with these sort of black holes in metamathematics, which are decidable theories, and which the proofs are not infinite. Normally, as you wander around the universe, most paths you might take in the universe can go on for an infinite time, unless you happen to run into a space-time singularity in a black hole, in which case you're stuck and your path will end, and it goes for only finite time. And the analogy to that is most proofs in sort of arbitrary mathematics, most proofs are potentially infinite and can just wander around metamathematical space. And I think and so one thing that's sort of fun there is, one view of physics is that sort of the end of the universe consists of a bunch of black holes that have been created by gravitational collapse as a result of sort of having too much energy in one place. Well, then the question is the end of mathematics, the infinite limit of mathematics, after, we've proved about 3 million theorems in the literature of mathematics so far in human mathematics. If you take the limit of mathematics as t goes to infinity, when we've proved trillions or an infinite number of theorems, what does that limit look like? And I think it's bizarrely similar to the limit of physics, because I think what ends up happening is that you inevitably sort of pack in proof density ends up being the analog of energy. Proof energy in physics is essentially proof density in mathematics. And you end up having, probably not fully worked out yet, you end up having things like the singularity theorems of physics about the inevitability of forming black holes. Similarly, there are, I think, similar ones in mathematics about the inevitability of sort of piling on enough results that you end up getting a decidable theory. And so you end up with these sort of metamathematical black holes as sort of the end point of mathematics. I could talk about all kinds of other analogies. There's another rather interesting one which has to do with the homogeneity of metamathematical space. In physics, one of the non-trivial facts is that motion is possible. You can take an object and you can just move it, and it isn't a different object when you moved it. It's if you are near a space-time singularity, that no longer works. But most of the time, in most parts of the universe, there is a notion of pure motion. You can just take things and move them around, and they don't change. What's the analog of that in metamathematics? Well, the analog of that has to be that you can essentially take a structure in one that is looked at in terms of one type of mathematics and move that structure, quotes, unchanged to another type of mathematics. And so this is kind of we kind of suspect that this has things to do with a lot of exciting dualities and correspondences between different areas of pure mathematics. And we're trying to do a bunch of empirical metamathematics to try and validate that. It's kind of a weird thing that you can do experimental science in mathematics as you can do experimental science in physics, so to speak, and trying to validate the claim that, for example, there's a certain amount of homogeneity in metamathematical space, which inevitably causes there to be sort of correspondences between very different kinds of mathematical theories. All right, I'd better stop there, and I'm happy to try and have questions, discussions, suggestions.